So in the previous two examples, we looked at intrinsic electric fields surrounding biological membranes. And for the next examples, we're going to look at the modulation of membrane potentials by external fields. And this is related to the subject of dielectric spectroscopy. So we have actually different physical mechanisms that can affect the dielectric response of living cells, whether in suspension or a tissue region. This little figure here denotes a living cell surrounded by positive charges. If we put on an electric field, that'll cause a redistribution of the charges, and an electric dipole moment is going to result here. Now, the actual motion of charges in the solution or a tissue region will give rise to what's called the alpha range in the dielectric response, and this can be actually quite high. The effective permittivity the relative permittivity can reach roughly 10 to the 7 in solution. But the permittivity of each individual region is with never greater than 78. However, it's the effective permittivity that's enormous here. Now, there's another mechanism. It's the Maxwell-Wagner effect, and that's due to the fact that we have potential differences developed across regions of differing permittivity. And this is, in fact, what we'll simulate in QuickField. There's another range in the dielectric property. It's called the gamma, and that is due to the rotation of dipole moments. For example, water has a dipole moment, and it will have a dielectric response all of its own. Okay. So let's look at a model here. And the model is called Mitosis. This is the geometry. I'll make it full screen once again. And in this model, we have axial symmetry with the z-axis is running along the bottom of the page. And now we have two ellipsoidal cells that I've put in here. I have exaggerated the membrane thickness so we can do this a little more rapidly. And however, the size here is still on the order of microns, so each one of these is roughly, these look like roughly 20 microns in length. Now I have two cells, so these could have just undergone a mitosis here. They separated. Now this is an AC conduction problem. So we're going to have an AC current flowing. This is the cytoplasm region. This is the external medium, and the external medium I have a electric permittivity of 80, electric conductivity of 1. The membrane has a permittivity of 12 and a very small electric conductivity. So membranes are very good insulators. They're lipid bilators. Now this is the edge of the solution region, so you can think of this as like a cylinder. It's rotated about here. And I've assigned a 0 normal current density to the edge of the cylinder. Okay. Now on each side of the model, I've assigned opposite potentials, and this is roughly negative 0.1 millivolts to the right and 0.1 millivolts to the left. Now, you might be able to see that this problem has an additional symmetry because these are opposite potentials. The central boundary will be an equipotential of 0 volts. So I could just as accurately model this problem by discarding half of it and assigning a 0 voltage boundary condition directly in between it. However, it doesn't take very long to solve the problem, and we'll just leave it here for visual effect. Let's see how many nodes we have. This is, if I go to properties here, I can see the number of nodes. Roughly 23,000 nodes, almost 24,000 nodes. So let's solve it. It's actually been solved, but we want to go ahead and solve it again. Okay, that was roughly 7 seconds. Okay, now this is an AC problem, and we have a, if we go to the problem properties, the frequency I have assigned is 10 hertz. Once again, it's axisymmetric. And we can see that these are the equipotentials. The electric field lines are going to be perpendicular to the equipotentials. And the current is going to be flowing along the model here from the plus to the minus. And the electric field and the current has been screened from the interior of the cells here. And furthermore, we have an amplification of the external field across each cell. And if I zoom in here, I can see the color represents the electric field strength, so we can see that that has been amplified. And if I make a contour that spans the membrane here, I can look at the field across the contour, and we can see that the electric field is very small outside of the membrane, and across the membrane is this is the induced electric field now due to the electrical excitation. So this is different from the intrinsic electric field that we've looked at previously. Okay. So what I'd like to do is illustrate the problem at a higher frequency, and I can clear this contour here. You can clear contour and go back to full screen mode. And what I'm going to do is I'm going to change the properties. Instead of 10 hertz, we'll look at high frequencies. So I'll make this 10 to the 10 hertz, the 10 gigahertz, and we can resolve the problem. Okay, loading. Now at high frequencies, you can see that the equipotential lines are now present inside of the cell, and in fact the electric field and the current are now penetrating the cell here. And I can make a plot of, say, for example, the electric field strength or any of the current components. Okay, so there you see the electric field. Furthermore, we can animate the solution and look at the electric field at different cycles, because this is an AC cycle, so the electric field is going to be changing direction as we excite the cell sample here. And then we can stop the animation.